The universe was not supposed to build giants this fast. We were told the early cosmos was a dim nursery, a fog of hydrogen, a slow gathering of light, tiny galaxies cautiously assembling themselves over hundreds of millions of years. But when the James Webb Space Telescope opened its golden eye and looked deeper than any instrument before it, it did not find fragile infants. It found monsters. Galaxies so massive, so mature, so impossibly large that they seem to have skipped childhood entirely. Systems containing tens of billions of stars may be more appearing when the universe itself was barely out of its own infancy. According to the rules we thought governed cosmic growth, these structures should not exist. And yet, there they are, bright, heavy, already grown. So we have to ask a dangerous question. Did the universe break the rules? Or did we misunderstand them? To feel what Webb saw, we have to rewind. Back past Earth, past the Sun, past the Milky Way, back 13 billion years to a time when the entire observable universe was less than 5% of its current age. Imagine compressing the 13.8 billion year history of everything into a single calendar year. On that scale, these galaxies appear in early January, not autumn, not summer, January, before cosmic structures were supposed to have enough time to gather, merge, ignite, and stabilize. And yet they shine like cities already fully built. We expected small, chaotic clumps proto-galaxies slowly merging like droplets of water on glass, gravity pulling hydrogen inward, the first stars igniting, supernovae enriching space with heavier elements, a gradual, hierarchical climb from small to large. Instead, Webb detected galaxies already containing the mass of our Milky Way, when the universe was less than 700 million years old. 700 million sounds enormous on human scales. It is longer than animals have walked on land, longer than complex life has existed, but cosmically, it is a blink. Gravity needs time to pull matter together. Stars need time to form, burn, explode, recycle material and build heavier generations. Black holes need time to grow by feeding. Yet these galaxies look like they had no patience for process. Some estimates suggest stellar masses exceeding 10 billion suns. Some candidates appear even larger. That is not a small statistical error. That is like discovering a fully grown redwood forest where there should only be seeds. We are not talking about a slight miscalculation. We are talking about acceleration. To build something that massive so early, gas would have had to collapse into stars at rates far beyond what our models predicted. Star formation efficiencies approaching theoretical limits, matter converting into light with ruthless speed. It is as if the early universe skipped rehearsal. Now picture where we stand while observing this. We are a species on a rocky planet, orbiting a middle-aged star, inside a spiral galaxy that took billions of years to assemble. We required 4.5 billion years just to form Earth. Life required another 3.5 billion to become complex. Civilization emerged in the last 10,000. And yet these galaxies, seen at cosmic dawn, were already massive long before Earth existed, long before the Sun ignited. They were ancient before we were possible. Webb did not stumble upon one anomaly. It found many candidates, bright, compact sources in the deep field, light stretched into infrared by cosmic expansion, travelling for over 13 billion years before touching a mirror floating 1 million miles from Earth. Each photon began its journey when the universe was dark, dense, and young. Each photon carried a contradiction. Because under the standard cosmological model lambda CDM, our best large-scale description of reality structure grows hierarchically. Small dark matter halos form first. They merge. Gas cools. Stars ignite. Feedback from supernovae and black holes regulates growth. It is messy, violent, but gradual. There are limits. Too much star formation too quickly, and radiation pressure pushes gas away. Supernovae explode and halt collapse. Black holes inject energy into their surroundings. Nature has brakes. Yet these early galaxies appear to have pressed the accelerator. So either they are not as massive as they look, or star formation was far more efficient than we believed, or dark matter behaved differently, or something subtle in our understanding of early physics needs refinement. Notice what is not on that list. Physics is wrong. The equations governing gravity, nuclear fusion, and cosmic expansion still describe everything from falling apples to orbiting planets to merging black holes with astonishing precision. But models are maps, not territory. And Webb may have shown us that the early terrain was steeper. Consider the conditions just after the Big Bang. The universe was hotter, denser. Fluctuations in matter density, tiny ripples in the cosmic microwave background seeded future structure. Regions slightly denser than average pulled in more matter. Gravity amplified differences. Those ripples were small, 1 part in 100,000. From that faint unevenness came everything stars, galaxies, us. To grow a massive galaxy quickly, those early overdensities must have collapsed faster than anticipated. Gas must have cooled efficiently. Star formation must have surged. Imagine pouring sand into shallow depressions. Normally, dunes form gradually, but what if the sand was stickier? What if gravity pulled harder in specific regions? What if the first stars formed larger, lived faster, died sooner, seeding space with heavy elements that allowed subsequent stars to form even more rapidly? Acceleration compounds. If the first generation of stars, population 3 stars, were extremely massive, they would burn hot and die young, exploding within a few million years. Their supernovae would flood surrounding gas with metals, enhancing cooling. Cooler gas collapses more easily. More collapse means more stars. A feedback loop. Not a violation, but a surprise in magnitude. And this is where the human frame tightens. We have always told ourselves a story of gradualism. Mountains rise slowly. Evolution crawls forward. Civilizations build brick by brick. Even the universe, we assumed, assembled patiently. Webb is whispering something different. Sometimes, under the right conditions, reality surges. If these galaxies truly are as massive as initial measurements suggest, then the early universe was not merely a nursery. It was a forge. And the forge burned hotter than we predicted. To understand how shocking that is, we have to feel the clock. 700 million years after the Big Bang sounds generous until we measure what had to happen inside that window. First, the universe had to cool enough for neutral hydrogen atoms to form. That alone took about 380,000 years. Before that, everything was a blinding plasma fog. Light could not travel freely. Space itself was opaque. Then came the long dark ages. No stars, no galaxies, just expanding hydrogen and helium, gravity slowly amplifying tiny density differences. Eventually, the first stars ignited likely a few 100 million years in enormous, metal-free, unstable. They burned like cosmic flashbulbs and died quickly. Their explosion seeded space with heavier elements, carbon, oxygen, iron, the ingredients needed for more complex star formation. Only after that could galaxies begin assembling in earnest. Now compress that into 700 million years. From darkness to tens of billions of stars. For comparison, our Milky Way has been forming stars for over 13 billion years and contains on the order of 100 billion stars. It is sprawling, 100,000 light-years across. It took time, mergers, collisions, gradual accumulation. But Webb is peering back to galaxies that, relative to their age, appear unnervingly mature, compact, bright, dense with stars. Some early analyses suggested stellar masses rivaling the Milky Way perhaps 10 to 50 billion solar masses, when the universe was only 5% of its current age. That is like walking into a newborn city and finding skyscrapers already finished. Lights on, traffic moving. So how could that happen? The answer begins not with stars, but with something invisible. Dark matter. We cannot see it, we cannot touch it, but its gravity dominates the large-scale structure of the universe. Ordinary matter, the atoms that make up you, me, planets, stars, accounts for only about 5% of the cosmic energy budget. Dark matter makes up roughly 5 times more. In the early universe, dark matter clumped first. It does not interact with radiation, so it was free to collapse into gravitational wells while normal matter was still trapped in plasma. Think of dark matter as the scaffolding. Hydrogen gas fell into those gravitational valleys once the universe cooled. The deeper the valley, the more gas it could capture. If those valleys formed faster or grew larger than expected, everything else could accelerate. Computer simulations based on lambda CDM predicted a certain distribution of dark matter halos at early times. Small halos first, then mergers building larger ones. Webb's observations suggest there may have been more massive halos earlier than anticipated, or that gas within them converted to stars with extraordinary efficiency. Efficiency is the key word. Under typical conditions, only a fraction of available gas turns into stars. Stellar radiation heats surrounding material. Supernova explosions blow gas outward. Black holes at galactic centers inject energy, regulating growth. These feedback mechanisms act like cosmic thermostats. But what if, in the dense early universe, those thermostats behaved differently? Higher overall densities mean gravity had more leverage. Gas streams between halos could have been thicker, colder, and more continuous. Instead of sputtering star formation, the early environment may have fed it relentlessly. Picture rivers of hydrogen pouring into a forming galaxy, uninterrupted, no long pauses, no gentle trickle, a sustained flood. Stars ignite. Massive stars explode within a few million years. Their shockwaves compress nearby gas rather than dispersing it, triggering even more star formation. A chain reaction. Some models now suggest that star formation rates in these primordial systems could have been tens or even hundreds of times higher than typical galaxies today. Relative to their size, that does not break physics. It stretches our expectations of how extreme early conditions could be. There is also the possibility that we are misjudging what we are seeing. When light travels 13 billion years to reach us, it is stretched by cosmic expansion. Visible light shifts into infrared. Webb was built precisely to capture that stretched light. Its segmented gold mirror, spanning 6.5 meters, gathers faint photons that began their journey before Earth existed. But interpreting that light requires models. Brightness translates to stellar mass only through assumptions about stellar populations, dust content, and age. If early stars were unusually massive and luminous, a galaxy might appear heavier than it truly is. Imagine mistaking a city of bright floodlights for a city of countless homes. Follow-up spectroscopic studies are refining these mass estimates. Some early candidates have been revised downward. Others remain stubbornly large. Even revised values, though, often exceed pre-Webb predictions. And here is where the tension becomes electric. Cosmology is not fragile. The standard model has survived decades of scrutiny. It explains the cosmic microwave background with exquisite precision. It predicts large-scale galaxy distribution. It matches observations of gravitational lensing and cosmic expansion. It works, but works does not mean complete. Webb's deep field images show hundreds of tiny red smudges galaxies so distant their light left when the universe was young. Each smudge is a system of stars, gas, dark matter, and likely a growing black hole. Yes, black holes. If galaxies were forming rapidly, their central black holes may have been growing rapidly too. Some quasars observed less than 1 billion years after the Big Bang contained black holes, with masses exceeding 1 billion suns. To grow that large so quickly, black holes must either start from massive seed objects or accrete matter at near the theoretical maximum rate. Again, acceleration. It is not that the universe is violating its own rules. It is that the early universe may have been far more intense than our calm, modern cosmic neighbourhood suggests. When we look at the Milky Way's serene spiral arms, we see a mature system. Star formation here is measured, regulated. We orbit quietly, one star among hundreds of billions. But go back 13 billion years, and conditions were compressed. Denser matter, shorter distances between structures, stronger gravitational interactions. The early universe was crowded, and crowded environments produce rapid outcomes. There is something deeply human about this revelation. We tend to project our current experience backward, because our galaxy grows slowly now. We assumed it always did, because stars formed gently in nearby nebulae. We assumed early star formation followed similar rhythms. Webb reminds us that youth can be explosive. Our own planet's history supports that. The early Earth endured asteroid bombardment, volcanic oceans, unstable atmospheres. It was not the calm blue world we know. Stability came later. The cosmos may follow a similar pattern. Violent youth, measured maturity, and we, fragile observers on a small planet, are peering across 13 billion years to witness that adolescence in real time. The photons hitting Webb's detectors tonight left their galaxies when those systems were barely formed. Those photons crossed expanding space, survived gravitational distortions, slipped past intergalactic hydrogen clouds, and finally struck gold-coated mirrors cooled to near absolute zero. They are messages from an era we never expected to look so developed. The universe did not wait politely. It built. Fast. And we are only beginning to understand how. If you want to feel how radical this is, imagine standing inside one of those early galaxies. Not as an abstract observer looking at a red smudge on a screen, but there, inside it, the sky would not look like ours. There would be no calm spiral arms stretching elegantly across 100,000 light-years. No slow, dignified rotation taking hundreds of millions of years per turn. These early systems appear compact sometimes, only a few thousand light-years across, yet packed with billions of stars. Take the Milky Way and compress much of its stellar mass into a region 10 to 20 times smaller. Now step inside. The night would not be dark. Stars would crowd the sky, far closer together on average. Massive, hot. Blue stars, far more common in the early universe, would flood space with ultraviolet radiation. Stellar winds would crash into one another. Supernovae would erupt regularly, perhaps every few years within a single galaxy. For comparison, in the Milky Way today, a supernova happens roughly once per century. In those primordial systems, the fireworks may have been relentless. You would not survive there. No planetary system stable long enough. No calm epochs for life to assemble. This was a cosmic construction zone. And that intensity matters. Because building stars is not just about piling up hydrogen. It is about managing energy. When gas collapses under gravity, it heats up. To continue collapsing into dense stars, it must cool efficiently, radiating energy away. In the early universe, cooling channels were limited. There were no heavy elements at first to help radiate heat. That is why early star formation was predicted to be slower, more inefficient. But once the first stars exploded and seeded space with metals, cooling became dramatically easier. Gas clouds could fragment into smaller clumps. More stars could form in parallel. If that enrichment happened rapidly, if early massive stars lived and died in quick succession, then the entire star formation engine could have shifted into high gear sooner than expected. Think of striking a match in a dry forest. One flame becomes many. And here is where Webb's data grows even more intriguing. Some of these early galaxies show signs of surprisingly mature stellar populations. That means not only did stars form quickly, they may have formed earlier than we anticipated. Push the timeline back. Maybe significant star formation began just 200 to 300 million years after the Big Bang. That is cosmically immediate. At that epoch, the universe was still transitioning from opaque to transparent. Neutral hydrogen-filled space. Ultraviolet light from the first stars gradually rionized that hydrogen in a process called cosmic rionization. Webb's discoveries intersect directly with that era. If massive galaxies existed early, they could have played a major role in rionizing the universe, flooding intergalactic space with high-energy radiation, transforming it from a neutral fog into the transparent cosmos we observe today. In other words, these galaxies were not just passive structures. They may have been architects of the universe's visibility. There is something poetic about that. The same systems that surprise us now may have been responsible for making the universe see-through in the first place. But the tension remains: how do you grow something so large, so fast, without bending the framework of cosmology? One possibility lies in the statistics of rarity. The universe is vast. Even in its early phases, small regions could have been unusually dense rare peaks in the distribution of matter. Most of space may have followed the expected slow build-up, but a few exceptional pockets could have collapsed earlier, feeding star formation at extreme rates. Webb, with its unprecedented sensitivity, might simply be detecting those rare overachievers. If so, we are not witnessing a universal rule change. We are witnessing the extremes of possibility, and extremes are often where reality feels impossible. Consider Mount Everest. Most of Earth's surface is near sea level, but one tectonic collision zone produced a peak nearly 9 kilometers high. Rare does not mean forbidden. It means statistically uncommon. Perhaps these galaxies are the Everests of the early universe. But even that analogy stretches, because we are not talking about 1 or 2 peaks. We are talking about a growing population of candidates. As surveys expand, more massive early galaxies appear. Some have been reclassified after detailed spectroscopic analysis, their distances refined, their masses adjusted, a few initial claims have softened. Yet the pattern persists. Galaxy assembly may have proceeded faster and more efficiently than pre-Webb simulations predicted. And simulations are not trivial toys. They incorporate dark matter evolution, gas dynamics, radiative cooling, star formation recipes, supernova feedback, black hole growth, all governed by equations tested across cosmic history. For those models to underpredict early massive galaxies means some ingredient, perhaps subtle, perhaps profound, needs recalibration. Not destruction. Refinement. Maybe dark matter halos merged more rapidly in dense environments. Maybe gas accretion from cosmic filaments was smoother and colder, minimizing energy losses. Maybe feedback processes were less disruptive in compact systems. Or maybe the initial mass function, the distribution of star masses at birth, was skewed toward heavier stars early on. More massive stars mean more light per unit mass, which affects how we estimate total stellar content. Each adjustment preserves physics, but each adjustment reshapes our narrative of cosmic dawn. And this is where the human perspective tightens again. We are not just adjusting equations, we are adjusting the origin story of structure. For decades, textbooks depicted the early universe as a gradual ladder, small halos first, then larger galaxies, then clusters, a steady climb. Webb suggests some rungs may have been skipped. What does that do to our sense of inevitability? If galaxies can surge into maturity within a few 100 million years, what else in the cosmos accelerates under the right pressure? There is a deeper pattern emerging. Complexity does not always crawl. Under extreme density, extreme gravity, extreme energy, systems can reorganize quickly. Thresholds are crossed, new phases ignite. The early universe was not calm clay waiting to be sculpted. It was compressed potential. And once the first structures tipped the balance, gravity amplified everything. Now zoom out. These galaxies are so distant that their light is faint beyond intuition. Webb detects photons with energies billions of times weaker than what your eyes perceive in daylight. It must shield itself from the sun, cool its instruments to cryogenic temperatures, and float 1,000,000 miles from Earth to avoid thermal noise. All of that engineering at the edge of possibility just to glimpse these early systems. We built a machine to see the beginning, and the beginning looked bigger than expected. You can feel the inversion. We assumed we were looking back at simplicity. Instead, we found ambition. Galaxies assembling with urgency. Stars igniting in crowded skies. Black holes feeding in compact cores. It does not feel like a gentle dawn. It feels like a surge. And the more we look, the more that surge refuses to shrink back into our comfortable expectations. There is a moment in every scientific era when the data stops behaving politely. Not catastrophically, not in open rebellion. Just insistently. Webb's early galaxy discoveries feel like that moment. Because the deeper we stare into cosmic dawn, the more the universe seems to whisper you underestimated me. To appreciate why this matters, we need to feel how tightly constrained the early universe actually was. After the Big Bang, the total amount of matter was fixed. The density fluctuations were mapped with exquisite precision by the cosmic microwave background radiation released when the universe was just 380,000 years old. Satellites like COBE, WMAP, and Planck measured those ripples down to tiny fractions. Those fluctuations are the blueprint for all later structure. From that blueprint, cosmologists run simulations forward in time. Billions of virtual particles representing dark matter collapse under gravity. Gas flows into halos. Stars form according to recipes tuned to observe physics. Galaxies merge. Black holes grow. The simulations reproduce the large-scale universe astonishingly well. Filaments of galaxies stretching across hundreds of millions of light-years. Voids where matter is sparse. Clusters where thousands of galaxies swarm together. So when Webb reveals galaxies that appear too massive too early, it is not a casual discrepancy. It touches the initial conditions. Because to grow faster, you either need more efficient star formation, more massive early dark matter halos, or a slight shift in how those primordial fluctuations evolved. Even small adjustments ripple forward dramatically. Imagine nudging the starting position of a domino chain by a centimetre. By the time the sequence reaches the 100th domino, the path has diverged entirely. But here's the crucial point. Nothing Webb has found requires tearing down the cosmic blueprint. The cosmic microwave background still matches the lambda CDM model with stunning accuracy. The expansion rate of the universe, governed by dark energy, still aligns within measurable tension ranges. Gravitational lensing still maps dark matter's invisible scaffolding. The foundations hold. But the early chapters may have been more intense. And intensity changes narrative. Consider how galaxies grow today. The Milky Way forms about 1 to 2 solar masses worth of stars per year. That's modest. It has enough gas to continue at that pace for billions of years. It's stable. But some early Webb galaxies may have formed stars at rates exceeding 50 or even 100 solar masses per year, despite being far smaller systems. That's like a small town building skyscrapers at the pace of Manhattan. And because these galaxies are compact, their gravitational wells are steep. Gas falling inward converts gravitational potential energy into heat and radiation. Starburst episodes ignite. Supernovae detonate. Shock waves propagate. But in dense environments, shock waves can compress nearby gas instead of dispersing it. Feedback becomes fuel. There's a threshold where chaos organizes into acceleration, and early cosmic density may have crossed it. Now let's bring in another actor black holes. At the centers of most galaxies reside supermassive black holes. Ours, Sagittarius, a star, has about 4 million times the mass of the Sun, modest by cosmic standards. But quasars observed less than 1 billion years after the Big Bang host black holes exceeding 1 billion solar masses. 1 billion! To grow from a stellar mass seed, say 100 solar masses, to 1 billion in under 700 million years requires sustained, near-limit accretion. The theoretical ceiling, called the Eddington limit, defines how fast matter can fall into a black hole before radiation pressure pushes it away. These early black holes seem to have lived at that limit or started from much larger seeds. Some models propose direct collapse black holes, enormous gas clouds collapsing directly into black holes of 10,000 to 100,000 solar masses without first forming stars. If such seeds were common, early black hole growth accelerates dramatically. And black holes influence galaxies. As matter spirals into a black hole, it releases immense energy. That energy can regulate star formation, but under certain conditions. It can also compress surrounding gas. Again, thresholds. Again, acceleration. The early universe may have been a place where multiple growth engines aligned at once. Dark matter halos forming early and rare dense peaks. Gas accreting efficiently along cosmic filaments. Massive stars forming and exploding rapidly. Black holes igniting and feeding. Radiation ionizing the surrounding medium. Instead of a gentle, staggered assembly, cosmic dawn may have been a synchronized surge. And we're only seeing it now because Webb can see the infrared glow of stretched starlight with unprecedented clarity. There's something profoundly human about this pattern. We assumed the early universe would resemble the quiet outskirts of today's cosmos. But we forget youth is rarely quiet. Think about human civilization. For tens of thousands of years, progress was incremental. Then agriculture ignited population growth, cities formed, industrialization exploded energy usage, the digital revolution compressed communication into milliseconds. Acceleration often hides inside early instability. The universe may have followed a similar arc. When matter density was higher, distances smaller, gravitational interaction stronger, processes that now unfold leisurely could have erupted. And here is the part that truly destabilizes intuition. If galaxies assembled faster than predicted, then structure formation is more efficient than we thought. Which means the raw potential of matter to organize itself under gravity is even more powerful than our conservative model suggested. Gravity does not need to break its laws. It only needs opportunity. Now picture yourself on Earth, looking up at the night sky. Every star you see belongs to a galaxy that took billions of years to form. But somewhere in the depths of space, light is arriving tonight from galaxies that matured before the sun existed. Their photons left when Earth was not even dust. Those photons crossed 13 billion years of expanding space stretching from ultraviolet into infrared, finally landing on Webb's cold detectors. We built a machine to listen to ancient light. And ancient light told us, the beginning was not small for long. It was ambitious. It built quickly. And perhaps that should not surprise us. Because from the tiniest quantum fluctuations, 1 part in 100,000 emerged everything. Stars, planets, life, you. If such vast complexity can arise from such faint ripples, maybe rapid growth is not an anomaly. Maybe it is a feature, but we are not finished. Because as Webb continues its surveys, the data becomes sharper. Distances are confirmed spectroscopically. Mass estimates are refined. Star formation rates are measured more precisely. Some early impossibly massive galaxies shrink under scrutiny. Others remain stubbornly large. And with each confirmation, the question tightens. How far can early growth stretch before it forces us to adjust the cosmic recipe? The universe is not breaking, but it is revealing edges. Edges where our confidence softens into curiosity. And curiosity is not weakness. It is propulsion. Because if the early universe could assemble giants in the dark, if gravity could orchestrate such rapid complexity under extreme conditions, then our picture of cosmic dawn is not collapsing. It is expanding. And expansion in this story has always been the rule. There is a deeper tension beneath all of this, and it doesn't live in telescopes or equations. It lives in expectation. For nearly a generation, we believed we understood the tempo of the early universe, not perfectly but confidently. The first stars ignite, small galaxies merge, Structure builds upward like a pyramid. Webb did not shatter that pyramid. It thickened its base. Because if galaxies with tens of billions of solar masses were already shining 500 to 700 million years after the Big Bang, then the climb from fluctuation to structure was steeper than we imagined. And steep climbs require force. Let's feel the force. Gravity is weak compared to other fundamental forces. A small magnet can lift a paperclip against the gravitational pull of the entire Earth. That comparison has been used to humble gravity for decades. But gravity has one advantage the other forces do not. It accumulates. It never cancels out. There is no negative mass to repel it, no gravitational charge that balances it. Every bit of matter attracts every other bit. Over cosmic distances and cosmic time, gravity becomes unstoppable. In the early universe, matter was closer together. The average density was far higher than today. That means gravitational attraction operated across shorter distances, with less empty space to dilute its pull. Imagine trying to assemble a crowd in a vast empty desert versus a crowded room. In the desert, people are scattered. It takes time for them to gather. In a crowded room, movement happens immediately. The early universe was that crowded room. Dark matter clumps formed early because they were not slowed by radiation. Once neutral hydrogen formed, ordinary matter fell into those clumps. But here is where Webb complicates the narrative. The rate at which gas cools determines how quickly it collapses into stars. Early on, cooling was inefficient at least until metals appeared. The first stars had to ignite in pristine hydrogen and helium environments. Those first stars were likely enormous, hundreds of times the mass of the Sun. Massive stars live fast and die young, exploding within a few million years. A few million years is nothing on cosmic scales. So if the first generation formed rapidly, exploded rapidly, enriched their surroundings rapidly, then the second generation of stars could form much more efficiently. The timeline compresses. Instead of slow build-up, you get cascading ignition. One cluster triggers another, one collapse seeds the next. Gas flows feed the cycle. And if dark matter holos were slightly more abundant in the high-mass tail of the distribution, even by a small statistical margin that effect multiplies, the rarest peaks in the density field would collapse first. And inside those peaks, growth could run hot. We often forget that the universe does not operate at the average. It operates everywhere, including in the extremes. Webb may simply be catching those extremes in the act. But even if these galaxies are rare overachievers, their existence still matters profoundly. Because rarity at cosmic scales is still enormous. If 1 in a million early regions formed massive galaxies quickly, that still means thousands across the observable universe. Thousands of early giants lighting up the darkness. And they were not isolated. They were connected by filaments, vast rivers of dark matter, and gas stretching across millions of light years. Gas doesn't drift randomly. It flows along these filaments, feeding galaxies from multiple directions. Cold streams of hydrogen could have funneled directly into galactic centers, bypassing some of the heating processes that slow star formation in modern systems. Think of arteries delivering uninterrupted fuel. Now add another layer. As galaxies grow rapidly, they generate intense radiation fields. That radiation ionizes surrounding hydrogen, carving out bubbles in the intergalactic medium. As more galaxies ignite, these bubbles overlap, eventually reionizing the entire universe. Reionization is one of the great transitions in cosmic history. It transformed the universe from opaque fog to transparent vastness. If early massive galaxies were more common than predicted, they may have driven reionization more aggressively. The timeline of transparency shifts. And that affects how light travels, how structures evolve, how subsequent galaxies form. Small adjustments in early growth echo forward billions of years. There is a reason cosmologists are both excited and cautious. Because Webb's discoveries do not point to a broken universe. They point to a more efficient one. And efficiency challenges our intuition. We assume complexity requires time, but sometimes complexity requires density. The early universe had density in abundance. Now let's return to something personal. You are made of elements forged in stars, carbon in your cells, oxygen in your blood, iron in your hemoglobin. Those elements were produced by generations of stars living and dying over billions of years. But if early galaxies formed rapidly, then heavy elements began enriching the cosmos earlier than expected. That means the raw ingredients for planets, chemistry, maybe even primitive life-enabling environments appeared sooner. The universe may have become chemically mature faster. We are not saying life emerged 13 billion years ago. We are saying the stage may have been set earlier than we thought. And that reframes the cosmic story. Instead of a slow awakening stretching over eons before complexity was possible, the universe may have entered its creative phase quickly. The first billion years were not idle. They were transformative. Webb is revealing a universe that did not hesitate. And here is the subtle shift happening inside the scientific community. Before Webb, simulations were tuned to match observations from the Hubble Space Telescope and ground-based surveys. Hubble could see far but not as deeply into infrared. Its view of cosmic dawn was limited. Webb extended that horizon dramatically. Suddenly, what was once theoretical territory became observable. An observation outruns assumption. Already, simulation teams are updating models, increasing resolution, refining star formation recipes, exploring alternative feedback strengths, testing different initial mass functions. Not because physics failed, but because nature revealed a more extreme parameter space. That is the heartbeat of science. Prediction, observation, adjustment, expansion. The universe did not defy its laws. It revealed their full range. And the more we look, the more that range feels vast. These early galaxies are not quiet footnotes. They are signals. Signals that gravity, under the right conditions, can sculpt structure with astonishing speed. Signals that the cosmic dawn was not dim and hesitant, but bright and ambitious. And perhaps, in that ambition, we recognize something familiar. Because from compressed beginnings, from dense, unstable origins, sometimes the most extraordinary growth emerges. The early universe may have been small, but it was never timid. There is a temptation, when confronted with something that feels too big, too early, too fast to reach for drama, to say physics is broken, to say everything we thought we knew is wrong. But the real story is subtler and far more powerful. Because what Webb is exposing is not fragility in the universe. It is elasticity. The equations that describe gravity have not changed since Einstein wrote them down. The behavior of hydrogen under pressure is the same in a laboratory as it was 13 billion years ago. Nuclear fusion ignites when temperature and density cross known thresholds. Those thresholds were always there. What Webb is revealing is that the early universe crossed them sooner, and in more places than we expected. To feel that properly, we need to zoom out even further. The observable universe today spans about 93 billion light-years across, but when the light from these early galaxies began its journey, the entire observable region was smaller than a fraction of that, compressed, denser, hotter. Space itself has been stretching ever since. So when we look at a galaxy that appears 13 billion light-years away, we are not seeing it as it is now. We are seeing it as it was when the universe was young, when distances between structures were tighter, when matter had not yet thinned into the vast emptiness we now inhabit. Density is destiny. Higher density means shorter gravitational timescales. Collapse happens faster. Interactions are more frequent. Mergers are more violent. The early universe was not just younger, it was crowded. Now imagine dark matter halos forming in that crowded environment. They begin small, perhaps containing millions of solar masses, but they merge rapidly. 2 halos collide, then 4, then 8. The mass compounds. Gas follows. Gas cools. Stars ignite. And once star formation begins in a compact region, radiation pressure and stellar winds carve cavities, compressing neighbouring gas clouds. It becomes self-propagating. We often describe galaxy formation as hierarchical small building blocks assembling into larger ones. But hierarchy does not mean slow, it means structured. Under the right conditions, hierarchical growth can cascade. Picture snow on a mountainside, and for hours, nothing dramatic happens. Snow accumulates quietly. Then one shift of vibration, a change in temperature, and the entire slope moves at once. An avalanche does not violate gravity. It fulfills it. The early universe may have been avalanche-prone, and Webb may be catching the aftermath. Some of the early galaxy candidates show compact morphologies, meaning their stellar mass is concentrated in small volumes. That concentration deepens gravitational wells, making it harder for gas to escape once captured. More gas retained means more fuel for stars. More stars mean more heavy elements. More heavy elements mean better cooling. Better cooling means more fragmentation into stars. The loop tightens. What once seemed like a bottleneck becomes a highway. Now layer in another subtle factor: cosmic variance. When we observe a tiny patch of sky, even a deep field, we're sampling a minuscule fraction of the total universe. That patch might coincidentally contain an overdense region, a proto-cluster environment where galaxies form earlier and grow faster than average. It's like looking at a single city during a population boom and assuming the entire planet is urbanizing at the same rate. As Webb surveys expand, astronomers are mapping larger areas, building statistics. Some regions appear more typical. Some remain extreme. But even if the most massive early galaxies are rare peaks, their mere existence stretches our model boundaries. And stretching boundaries is not a crisis. It is calibration. Consider how long humanity believed the Milky Way was the entire universe. Then we discovered other galaxies. Then we discovered the universe was expanding. Then we found dark matter. Then dark energy. Each revelation expanded scale. Each expansion felt destabilizing. But none destroyed physics. They refined it. Webb belongs to that lineage. It is not overthrowing cosmology. It is deepening it. Now bring the focus back to us. You're standing on a planet that formed 4.5 billion years ago, long after these early galaxies had already matured. Our sun ignited billions of years after cosmic dawn. The heavy elements in your body were forged in stars that themselves descended from those early stellar generations. There is a chain of ancestry stretching from those compact, hyperactive galaxies to your bloodstream. When Webb detects light from a galaxy 13 billion years old, it is not just observing structure. It is observing prehistory. Not human prehistory, elemental prehistory. The first chapters of chemical enrichment that eventually made rocky planets possible. And here is the quiet inversion in all of this. We assume that the early universe was too primitive, too chaotic, too sparse for rapid complexity. Instead, it may have been uniquely suited for it. High density, abundant fuel, extreme gravitational gradients, short interaction timescales. A perfect storm for accelerated assembly. It's almost uncomfortable. Because we like to imagine that complexity required patience. But the universe may have been capable of astonishing efficiency from the beginning. And that forces a deeper appreciation of gravity. Gravity does not rush. It simply persists. It pulls always. Given enough density, enough proximity, enough time, even if that time is short by cosmic standards, it sculpts structure inevitably. Webb has not shown us a reckless universe. It has shown us a decisive one. A cosmos that, when conditions aligned, moved quickly. And as we gather more data, the tension becomes productive. Simulation teams push models to higher resolution. Star formation recipes are revised. Black hole seeding scenarios are tested. Gas accretion pathways are re-examined. The scientific machine hums faster. Because the universe just handed it a challenge. And challenges are invitations, not to panic, but to explore the edges of possibility. The most important realization is this: there is still room inside our current framework for these galaxies to exist. The room is tighter than we thought, but it is there, and that makes this moment electric. We are watching cosmology evolve in real time, not because the universe contradicted itself, but because we finally built an instrument capable of seeing its most extreme youth. For centuries, we could only imagine the beginning. Now we are measuring it, and the beginning looks bold, not fragile, not hesitant, bold, which raises a quiet, thrilling possibility. If the universe was capable of such rapid growth in its first 500 million years, what other thresholds did it cross that we have not yet seen? What other extremes are waiting in the dark, just beyond our current horizon? Webb has only just begun to look, and already the story feels larger than we prepared for. There is another layer to this story that makes it even more destabilizing. Because galaxies are not just collections of stars. They are ecosystems. When we say massive galaxy, we are not just counting suns. We are talking about gravitational architecture, rotating disks or turbulent blobs, central black holes, stellar nurseries, magnetic fields, radiation pressure, dark matter halos extending far beyond visible light. To build one of these systems is to orchestrate billions of interlocking processes. And Webb is suggesting that orchestration was happening almost immediately. Think about the choreography required. Gas must fall inward without fragmenting too chaotically. Stars must ignite in enormous numbers. Supernovae must explode but not blow everything apart. Heavy elements must disperse but not escape. Black holes must form and grow but not sterilize their surroundings completely. It is a balancing act. Too much feedback, and star formation shuts down. Too little feedback, and gas collapses uncontrollably. Modern galaxies sit in that balance. But in the early universe, balance may have been dynamic, oscillating rapidly between collapse and explosion, compression and radiation. And that dynamism could drive speed. Imagine a heart beating faster under stress. The rhythm intensifies, circulation accelerates. Early galaxies may have pulsed like that. Now consider something else Webb has hinted at: surprising brightness. Some of these early galaxies appear more luminous than expected for their estimated mass. That brightness could mean several things. It could mean we are seeing intense starburst short-lived periods where stars form at staggering rates. It could mean the stellar populations are dominated by massive hot stars that emit enormous amounts of ultraviolet light. Or it could mean accreting black holes' active galactic nuclei are contributing significant radiation. Each possibility amplifies the sense of extremity. Because brightness is not passive. Brightness is energy. And energy reshapes environments. In the early universe, ultraviolet radiation from the first stars began tearing electrons off hydrogen atoms, ionizing the cosmos. This process did not happen evenly. It happened in patches, bubbles expanding outward from luminous sources. If early galaxies were more abundant or more intense than predicted, then the patchwork of reionization may have been faster, more chaotic, more interconnected. Webb is not just finding galaxies. It is mapping the first illumination of the universe. Now let's slow down and feel the scale again. When we look at one of these galaxies, we are seeing light that has travelled for more than 13 billion years. That light left when the universe was perhaps 500 million years old. At that time, the entire observable cosmos was compressed into a volume far smaller than it occupies today. Every cubic region was denser, every gravitational interaction had more leverage. Over the intervening eons, space expanded, galaxies drifted apart, star formation gradually slowed as gas reservoirs depleted. The universe matured, but Webb is giving us snapshots of adolescence. And adolescence is intense. If you could compress 13.8 billion years into a human lifetime of 80 years, These galaxies appear when the universe is barely 3 years old. 3. And already building structures that rival the Milky Way? That is the intuition violation. Not that galaxies exist, but that they exist so fully, so early. There is also an uncomfortable implication. If galaxies can assemble that quickly, then the window between no structure and complex structure is narrower than we thought, which means the transition from simplicity to complexity is sharper. Sharper transitions often hide tipping points. In climate systems, small changes in temperature can trigger massive shifts in circulation patterns. In ecosystems, these slight imbalances can cascade into rapid transformation. In cosmology, density fluctuations that cross a threshold can collapse rapidly. The early universe may have contained more regions perched near that threshold than our average-based models assumed. And when they tipped fast. But here is where discipline matters. Nothing Webb has shown requires exotic new forces. No evidence yet demands rewriting gravity. No data forces us to discard dark matter. Instead, the tension lives in parameters, in how efficiently gas turns into stars, in how quickly halos merge, in how massive the first stars were. These are adjustable within known physics, but adjusting them reshapes the story of cosmic dawn. And story matters. Because our understanding of how the first galaxies formed feeds into everything that followed. The distribution of elements, the growth of black holes, the formation of galaxy clusters, the evolution of the intergalactic medium, even the rate at which later galaxies like ours assembled. If early growth was accelerated, then downstream timelines compress slightly. Not catastrophically, but meaningfully. It is like discovering that the foundation of a skyscraper was poured in half the time expected. The building still stands, but the pace of its construction changes how you interpret the rest of the process. Now bring yourself back into the frame. You are made of atoms forged in stellar cores. The oxygen you breathe was created in massive stars that exploded long before the sun formed. Those stars were descendants of earlier generations. Trace that lineage backward far enough, and you approach these early galaxies. If they enriched the universe sooner, then the chemical evolution that eventually allowed rocky planets happened earlier too. The universe may have become hospitable, at least chemically, faster than we thought. Not comfortable, not life-friendly, but prepared. Prepared with carbon, nitrogen, oxygen, silicon. Prepared with the ingredients for complexity. And that changes the emotional texture of cosmic history. Instead of a long, empty prelude before creativity, we may be looking at a universe that entered its creative phase almost immediately. The first few 100 million years were not a quiet waiting period. They were a furnace. Webb is peering into that furnace. And what it sees is not disorder. It is ambition under pressure. Stars igniting in crowded cores, galaxies assembling in dense knots, black holes swelling in hidden centers. The universe was not hesitant. It was decisive. And as more data pours in, more spectra, more deep fields, more confirmed distances, the outline sharpens. Some early claims will soften, some will strengthen, the statistics will settle. But one thing has already shifted. Our expectation of how quickly the cosmos can organize itself. We once imagined the early universe as a slow climb out of darkness. Now we see flashes of rapid construction. Not chaos without structure, but structure emerging with urgency. And that urgency feels almost alive. Not because the universe has intention, but because gravity, under compression, wastes no time. Webb has not broken physics. It has revealed its tempo at the edge. And the tempo is faster than we dared to imagine. There is a quiet irony in all of this. For most of human history, the night sky felt permanent, fixed, unchanging. The stars appeared as pinpoints embedded in a dark dome. Ancient civilizations built myths around their stability. But when we finally developed the tools to look deeper, we discovered that the sky is not static. It is layered. Every faint red smudge in a Webb deep field is not just distant in space. It is distant in time. We are not looking across the universe. We are looking backward through it. And what we are seeing in those early layers is speed. To truly grasp the shock, imagine this. Before Webb, our clearest view of very early galaxies came from the Hubble Space Telescope. Hubble pushed the frontier to about 400 to 500 million years after the Big Bang. But at those distances, its sensitivity in infrared was limited. The earliest galaxies it detected were small, faint, tentative. They fit expectations. Webb changed the wavelength range. Infrared light, stretched by cosmic expansion, carries the signatures of ancient stars. Webb was designed to live in that red-shifted domain. Its mirror collects more than 6 times the light of Hubble. Its instruments can separate faint spectra from background noise with surgical precision. When Webb opened its eyes, it did not just see further, it saw differently. And almost immediately, candidate galaxies appeared at redshifts above 10, then above 12. Some even suggested redshift 15 or higher, meaning their light left when the universe was perhaps 300 million years old. 300 million. That is shorter than the time between the dinosaurs' extinction and today. In cosmic terms, it is nearly nothing. And yet inside that sliver of time, galaxies were already assembling at breathtaking scale. Some early photometric estimates suggested stellar masses up to 100 billion solar masses at redshifts above 10. That sent shockwaves through the community. Subsequent spectroscopic confirmations have refined many of those numbers downward. Some of the most extreme claims softened under closer analysis. But even revised masses remain substantial. Even if a galaxy contains only 10 billion solar masses at 500 million years, that is still astonishing. Because to reach 10 billion solar masses in stars, you must have processed far more gas. Not every bit of hydrogen becomes a star. Some remains diffuse, some is blown out by feedback, some never cools efficiently. The star formation engine must have been relentless. Now let's feel the energy budget. When a star forms, gravitational potential energy converts into heat and radiation. Nuclear fusion ignites, releasing enormous amounts of energy over millions or billions of years. Multiply that by billions of stars forming in rapid succession. The radiation fields inside these early galaxies must have been extreme. Ultraviolet light flooding space, stellar winds slamming into surrounding gas, shock fronts colliding and overlapping. And yet the galaxies did not tear themselves apart. That balance between explosive feedback and continued collapse is the heart of the puzzle. Why didn't early starbursts sterilize their own fuel supply? One possibility is geometry. Gas in the early universe may have accreted along narrow, dense filaments. When stars exploded, their energy could vent outward perpendicular to those inflowing streams, allowing fresh gas to continue feeding the core. Imagine punching holes in the roof of a furnace while fuel keeps entering through the sides. Energy escapes, but the fire continues. Another factor could be turbulence. In modern galaxies, turbulence can either inhibit or enhance star formation. In dense early systems, turbulence may have compressed gas into pockets, where collapse happened faster than feedback could disperse it. And then there is metallicity. As the first generations of stars enriched their surroundings, cooling efficiency increased dramatically. Gas clouds could fragment into smaller clumps, leading to higher star formation rates. The universe may have transitioned from inefficient to hyper-efficient star production in a very short window. A threshold crossed, and once crossed, growth accelerated. Now bring this back to human scale. You live in a galaxy that feels ancient and stable. The Sun is middle-aged. The Milky Way's star formation rate is modest. The nearest supernova visible to the naked eye might happen once in a human lifetime if we're lucky. But imagine living inside one of these early galaxies. The sky would flicker with frequent stellar deaths. The radiation would be intense. The gravitational tides between merging substructures would warp the environment constantly. It would not feel like a serene cosmic landscape. It would feel like a city under construction, cranes swinging, foundations pouring, sparks flying. And yet from that turbulence came structure. Not chaos. Structure. That is the emotional core of Webb's discovery. The early universe was not fragile. It was fertile. And fertility under pressure breeds rapid growth. Now zoom out again. We are detecting perhaps dozens of candidate massive galaxies at extreme redshifts. The sample is growing, surveys are ongoing, spectra are being analysed. Each confirmation strengthens the case that early galaxy formation was more efficient than pre-Webb models assumed. But the overall cosmological framework remains intact. Dark matter still seeds structure, dark energy still drives expansion, general relativity still governs gravity. The difference is tempo. And tempo changes narrative. Because if the universe assembled complexity quickly once conditions allowed, then cosmic history is not a slow crawl from simplicity to sophistication. It is a series of accelerations, inflation and almost unimaginable burst of expansion in the first fraction of a second, recombination the sudden transparency of the universe, reionization the rapid illumination by early stars, galaxy assembly possibly faster and more intense than expected. The cosmos may not move evenly. It may surge. And we, billions of years later, are the descendants of those surges. The atoms in your body were forged in stars that trace their lineage back to those early star factories. You are not separated from cosmic dawn. You are downstream of it. Webb is not just showing us distant galaxies. It is showing us ancestral momentum. A universe that, from almost nothing but hydrogen and slight fluctuations, built vast stellar systems in a few 100 million years. That is not physics failing. That is physics operating at full capacity. And as we continue to watch as deeper fields reveal fainter structures, as spectroscopy sharpens mass estimates, as simulations evolve to match observation, one truth is already clear. The early universe did not hesitate. It built. And it built faster than we ever dared to picture. There is a moment when you stare long enough at Webb's deep fields, when the scale stops feeling abstract and starts feeling confrontational. Because those tiny red arcs and smudges are not theoretical constructs. They are cities of stars, each one potentially holding billions of suns, orbiting a central gravitational anchor, surrounded by dark matter halos extending far beyond visible light. And they were already there when the universe was barely beginning. Let's tighten the numbers again. The universe today is 13.8 billion years old. Webb is detecting galaxies at redshifts corresponding to 400 and 500, even 300 million years after the Big Bang. That means these systems formed within the first 3 to 5% of cosmic history. If the entire history of the universe were compressed into a single 24-hour day, these galaxies appear within the first hour. Within that first hour, gravity had to gather matter from near-uniform density into structures containing billions of stars. That is the violation of intuition, not impossibility. Speed? Now imagine the alternative. Suppose Webb had found only tiny, faint proto-galaxies, diffuse clouds just beginning to coalesce. That would have confirmed the slow, cautious narrative. Instead, we see brightness, compactness, maturity, which means the early density fluctuations, those faint imprints measured in the cosmic microwave background, must have evolved efficiently. Those fluctuations were only about 1 part in 100,000. From that almost imperceptible unevenness, everything grew. It is like starting with a nearly smooth ocean surface and, within minutes, watching skyscrapers rise from tiny ripples. The mathematics allows it, but emotionally it feels abrupt. There is another factor that intensifies this time dilation. When we observe distant galaxies, we are seeing them not only far away but at a time when cosmic expansion was occurring more rapidly relative to local structure growth. The Hubble parameter, the rate of expansion, was higher in the early universe, Space was stretching quickly. And yet, within that stretching space, gravity was still pulling matter together locally. It is a paradoxical dance. On large scales, everything expands. On smaller scales, matter collapses. The fact that collapse could outpace expansion in certain dense regions so quickly is part of the awe. Gravity won locally. Fast. Now let's consider what happens inside a rapidly assembling galaxy. As gas collapses toward the center, angular momentum causes it to spin. Rotation flattens gas into disks or turbulent rotating blobs. Collisions between gas clouds trigger star formation. Massive stars form and explode, enriching the medium. But rapid growth also means mergers. Small proto-galaxies slam into each other. Dark matter halos overlap. Tidal forces distort shapes. Gas funnels towards central regions during mergers, igniting starbursts. In modern times, we see this in colliding galaxies like the antennae. Star formation rates skyrocket temporarily. Now imagine the early universe, where mergers were not rare events separated by billions of years. They were common. Frequent collisions compress time, and compressed time accelerates evolution. The early universe was not a quiet laboratory. It was a crowded construction site, and the construction crews were gravity and gas. But here is the crucial stabilizing fact. Even with accelerated growth, the galaxy's Webb seas are not arbitrarily large. They are extreme relative to expectation, but they are still within plausible bounds given available baryonic matter and dark matter halo distributions. They do not exceed the total amount of matter allowed by cosmology. They push efficiency, not conservation. That distinction matters, because it means the universe is not breaking accounting rules. It is optimizing within them. And optimization under pressure produces elegance. Now let's bring the human frame back into focus. For centuries we have told the story of cosmic insignificance. We are small, we are late, we are peripheral. But Webb complicates that narrative too. Because if complexity can arise quickly under the right conditions, then our existence is not merely the product of endless delay. We are the outcome of a universe that organized itself rapidly from the beginning. The same gravity that pulled hydrogen into those early galaxies eventually pulled gas into the molecular cloud that birthed our sun. The same physics that accelerated star formation in cosmic dawn eventually forged the carbon in your cells. You are not the endpoint of a slow drift. You are part of a system that, once it began structuring itself, did so decisively. There is something deeply empowering in that, not because we are central, but because we are continuous. The acceleration that built early galaxies echoes in every star. And yet, mystery remains. Some Webb observations hint at galaxies that appear surprisingly chemically evolved, containing heavier elements earlier than expected. If confirmed broadly, that would suggest stellar processing cycles happened even faster than current models estimate. More explosions, as more enrichment, as more cooling, more stars. Each layer amplifies the sense of urgency in cosmic dawn. But caution is part of strength. Astronomers are carefully confirming redshifts through spectroscopy, splitting light into precise wavelengths to measure chemical signatures and distances. Photometric estimates can overstate mass, dust can mimic age, bright starbursts can skew interpretation. Science tightens the lens. Some candidates shrink. Others stand firm. And that is exactly how discovery should feel. Not reckless, not panicked, but electric. Because even after revisions, the pattern remains. The early universe was capable of assembling massive galaxies astonishingly fast. And every confirmation sharpens the implications. Simulations are being updated, initial mass functions are being reconsidered, feedback efficiencies are being recalibrated, dark matter halo statistics are being refined. The cosmic blueprint is not torn. It is redrawn with bolder lines. And we are watching it happen in real time. There is a strange beauty in this. We built a telescope to see the first light. And instead of simplicity, we found ambition. Instead of fragile beginnings, we found accelerated construction. Instead of delay, we found decisiveness. The universe did not crawl out of darkness. It surged. And we fragile, carbon-based observers on a small planet are privileged to witness that surge 13 billion years later. The photons that Webb collects tonight left their galaxies when Earth did not exist. They travelled across expanding space for nearly the entire history of the cosmos. And when they finally strike gold-coated mirrors and register as faint infrared signals, they carry one clear message. From almost nothing, gravity built giants. Quickly, there is a final psychological barrier we have to cross to truly understand what Webb is showing us. We instinctively associate early with primitive. Early humans were primitive compared to us. Early technology was primitive. Early life was simple. So when we say early universe, our intuition fills in the blank small, crude, unfinished. But the universe does not evolve like a civilization. It evolves like a pressure system, and pressure can produce extremes immediately. Right after the Big Bang, the universe was almost perfectly smooth, but not entirely. Tiny density differences existed. Gravity amplified them relentlessly. What matters is not how old the universe was. What matters is how compressed it was. At 500 million years old, the universe's average density was more than 100 times greater than today. 100 times. That changes everything. Higher density means shorter gravitational freefall times, the time it takes a cloud of gas to collapse under its own gravity. The denser the cloud, the faster it collapses. So while we measure time in years, gravity measures in density. And density was abundant. That is why the early universe could move quickly. Now consider the interplay between collapse and radiation. When gas falls inward, it heats up. That heat must escape for collapse to continue. In the first stars, cooling was limited to hydrogen and helium emission processes. But once even trace amounts of carbon and oxygen appeared, cooling channels multiplied. Cooling accelerates fragmentation. Fragmentation accelerates star formation. Star formation accelerates enrichment. It is a chain reaction. If the first generation of stars was extremely massive and evidence suggests many were then, their lifetimes were measured in millions, not billions, of years. They lived fast and died violently. Each death enriched surrounding gas. And once enrichment began, efficiency increased sharply. The early universe may have crossed from inefficient ignition to runaway star formation faster than we modelled. And if that transition happened widely, massive galaxies become less shocking. Still extreme, but understandable. Now layer in cosmic geometry. Dark matter does not distribute itself randomly. It forms a cosmic web of filaments connecting dense nodes. Galaxies grow at the intersections of those filaments. In the early universe, those intersections were fed continuously by cold gas streams flowing along filaments. Modern galaxies often experience hot mode accretion, where gas shock heats before cooling and collapsing. But early galaxies may have been dominated by cold mode accretion gas flowing directly into galactic centers without being heated to high temperatures first. Cold flows are efficient. They deliver fuel straight to the core. If early galaxies were bathed in uninterrupted cold streams, star formation could sustain astonishing rates. Now imagine standing at one of those filament intersections 13 billion years ago. Gas pouring inward from multiple directions, mergers happening frequently, supernovae detonating, black holes feeding. It would not look primitive. It would look intense. There is something else we must acknowledge. Webb's discoveries also remind us of observational humility. For decades, we extrapolated from limited data. Hubble's view of the early universe was extraordinary for its time, but it was like peering through a keyhole. Webb flung the door open. And when the door opened, reality did not conform neatly to the sketch we had drawn. That does not mean the sketch was wrong. It means it was incomplete. And incompleteness is not failure. It is invitation. Astronomers are now running simulations at higher resolution than ever before. They are adjusting parameters within physically allowed ranges. They are testing whether slight increases in star formation efficiency or variations in early stellar mass distributions can reproduce Webb's observations. Preliminary results suggest they can, but only if early conditions were pushed toward the high efficiency end of possibility. In other words, the early universe may have been operating near optimal gravitational throughput. Gravity wasted little opportunity. Now bring the focus back to you. You exist 13.8 billion years after the Big Bang. The Milky Way formed over billions of years through mergers and gradual accretion. The Sun ignited 4.6 billion years ago. Earth cooled, life emerged, evolution unfolded. All of that feels like deep time. But Webb is showing us that structural complexity, began almost immediately, which means the seeds of everything we know were planted early. Very early. The universe did not spend billions of years idling before it began building. It began building almost at once, and that realization shifts something subtle inside us. We often think of ourselves as latecomers to a long, slow cosmic story. But in truth, we are participants in a universe that moved decisively from simplicity to structure. The transition from smooth plasma to galaxies took less than 1 billion years. Less than 7% of cosmic history. After that, the large-scale scaffolding was in place. Everything else, clusters, superclusters, planetary systems, biology unfolded within that established framework. Webb is showing us the framework being erected. And it went up fast. There is no evidence that physics allowed the impossible. Instead, physics allowed the extreme. Given the right density, given sufficient fuel, given relentless gravity, the universe accelerated. And perhaps that should not shock us. Because from a tiny quantum fluctuation in the first fraction of a second after the Big Bang came all structure. If the universe could expand exponentially in a burst of inflation lasting less than 1/1,000,000,000th of a second, why should we be surprised that galaxies could assemble quickly when gravity had room to operate? The cosmos has always contained the capacity for dramatic change. Webb simply revealed one more example, and as the data deepens, as redshifts are confirmed, masses refined, spectra analysed, one theme becomes unavoidable. The early universe was not hesitant. It did not crawl cautiously toward complexity. It surged toward it. From faint fluctuations to blazing galaxies in a few 100 million years, from near uniform gas to gravitational architecture spanning thousands of light years, from darkness to structured light. And we, watching from a quiet spiral arm billions of years later, are finally beginning to see how bold those first moves were. There is something almost defiant about the images. We expected to look back and find fragility, the universe still learning how to hold itself together. Instead, Webb shows a structure that looks unapologetically established. Not finished, not modern, but already substantial. And that forces a deeper question. If galaxies could grow this quickly, what does that say about the nature of cosmic limits? We tend to imagine limits as hard walls. Maximum star formation rate, maximum black hole growth, maximum efficiency. But in physics, limits are often gradients, not cliffs. Take the Eddington limit, the theoretical balance point where radiation pressure pushing outward equals gravity pulling inward during accretion onto a black hole. It is not a brick wall. Under certain geometries, matter can exceed it temporarily. Gas can flow in clumps. Radiation can escape anisotropically. Nature bends toward efficiency when conditions align. The same may apply to galaxies. Star formation is regulated by feedback, but feedback depends on environment. In dense early systems, energy from supernovae might have escaped more easily in some directions, allowing collapse to continue in others. In other words, the brakes may not have been applied evenly. An uneven braking allows momentum. Now consider how quickly the cosmic web itself formed. Simulations show that within a few 100 million years, dark matter had already organized into filaments and nodes. Those nodes became gravitational hubs. If a region began slightly overdense even by a tiny margin, it could collapse early, pulling in surrounding matter at accelerating rates. Those rare peaks are statistically inevitable. And in a universe as vast as ours, rare still means many. Webb may be revealing not a violation of expectation, but the bright edge of probability. But probability at this scale feels dramatic. Because when you compress the timeline, every event feels amplified. 300 million years. 500 million years. These are vast numbers for us. Longer than mammals have existed. Longer than flowering plants. But compared to 13.8 billion years, they are the first breath. And within that first breath, the universe was already building cities of stars. Let's step inside one of those cities again. Billions of suns packed into a region a fraction the size of the Milky Way. Gravitational tides pulling stars into chaotic orbits. Gas clouds colliding at supersonic speeds. Ultraviolet radiation saturating interstellar space. Black holes at the centre feeding on infalling material, releasing jets and winds that carve channels through gas. It would not look stable. It would look alive with motion. And yet, from that instability, lasting structure emerged. Because gravity does not require calm to create order. It requires mass. Now bring the scale outward. These early galaxies did not exist in isolation. They were embedded in the expanding universe, which was cooling and thinning even as local collapse intensified. This duality is essential. On the larger scales, expansion dominates. Space stretches. Galaxies drift apart. On smaller scales, gravity dominates. Matter falls inward. The early universe was the battleground between those two tendencies. And locally, gravity won quickly. That victory created islands of structure in a sea of expansion. Over billions of years, those islands grew into clusters and superclusters. But Webb is showing us the moment the first islands rose above the cosmic tide. And they rose fast. There is another subtle implication here. If early galaxies assembled rapidly, then their stellar populations would evolve rapidly too. Massive stars burn their fuel in millions of years. They explode. Their remnants collapse into neutron stars or black holes. That means within a few 100 million years, the universe already contains stellar mass black holes, neutron stars, enriched gas clouds, and potentially even complex molecules. Chemical complexity began almost immediately after structural complexity. The cosmos did not linger in simplicity. It accelerated into diversity. And this acceleration reshapes how we think about cosmic habitability, not in the sense that life emerged instantly, but in the sense that the ingredients for complexity appeared earlier. Earlier enrichment means earlier rocky planet potential. Earlier heavy elements mean earlier dust formation. Dust allows cooling, which allows smaller stars to form stars that live billions of years. The seeds of long-lived stability may have been planted surprisingly early. Webb is not just revising galaxy formation. It is subtly shifting the timeline of cosmic readiness. Now pause and consider the audacity of what we're doing. A species that evolved on a planet orbiting an ordinary star has built a telescope that floats nearly 1 million miles from Earth, shielded from sunlight by a multi-layered sunshade the size of a tennis court, cooled to temperatures barely above absolute zero. All of that engineering just to capture faint infrared photons that began their journey when the universe was young. Those photons strike a gold-coated mirror, reflect into detectors, and become data. From data, we reconstruct the architecture of cosmic dawn. And what we reconstruct challenges our comfort with gradualism. The universe did not tiptoe into complexity. It leapt. Not recklessly, not chaotically, but decisively. And that decisiveness humbles us. Because it reminds us that our models are approximations of an engine far older and more capable than our intuition. Webb is not showing us a broken universe. It is showing us a universe operating at the high end of its performance envelope. Star formation near peak efficiency. dark matter halos collapsing in rare, dense peaks, cold gas streams feeding cores relentlessly, black holes growing at near their theoretical limits. Physics at full throttle. And the more we look, the clearer it becomes that Cosmic Dawn was not a dim rehearsal. It was an opening act delivered at maximum intensity, which leads to a final realization that is both unsettling and exhilarating. If the universe could assemble such massive galaxies so quickly, then the boundary between impossible and unexpected is thinner than we thought. Not because the laws change, but because their range is wider, and we are only beginning to explore it. There is one more shift we have to make, and it is subtle, but it changes everything. We have been asking, how did galaxies grow so fast? But beneath that question hides another. Why did we expect them not to? For decades, our models of early galaxy formation were calibrated against limited observation. We saw small numbers of distant objects, we inferred growth rates, we simulated plausible timelines. And within that framework, gradualism felt natural. But nature does not owe us gradualism. It owes us consistency. And consistency does not mean slowness. It means fidelity to physical law. Gravity, thermodynamics, radiation, they do not hesitate. They respond instantly to conditions. If density is high, collapse accelerates. If cooling is efficient, fragmentation multiplies. If fuel flows steadily, growth continues. The early universe had all three: high density, rapid enrichment, abundant cold inflow. Under those circumstances, why wouldn't structure assemble quickly? Our surprise says more about human intuition than cosmic reality, because we are creatures of moderate environments. On Earth, change feels slow. Mountains erode over millions of years. Continents drift at centimeters per year. Biological evolution unfolds across epochs. We are conditioned to equate scale with patience. But the universe in its youth was not patient. It was compressed. And compression amplifies dynamics. Think about a star collapsing at the end of its life. Over millions of years it burns steadily. Then, in seconds, its core implodes and rebounds in a supernova that outshines entire galaxies. Long preparation, sudden release. The early universe may have followed a similar arc, except the preparation phase lasted only a few 100 million years. Tiny fluctuations, gradual gravitational amplification, then threshold. And once threshold was crossed, growth cascaded. Now consider the cosmic microwave background again, that faint radiation from 380,000 years after the Big Bang. It contains the imprint of those initial fluctuations. We measure them precisely. But those measurements give us average behavior. The average density contrast, the average power spectrum. Reality, however, plays out in specific locations. And in some locations, the fluctuations were slightly stronger, slightly denser, slightly earlier to collapse. And when collapse begins in a dense region, it pulls in surrounding matter, deepening the overdensity further. A positive feedback loop. The earliest galaxies likely formed in those rare peaks. Webb is detecting the luminous descendants of those peaks. They are not typical. They are the early overachievers. But the existence of overachievers reshapes expectation. Because once you confirm they exist, your models must allow for them. And allowing for them means acknowledging that the universe's early growth curve had a steeper upper bound. Now let's confront something even more destabilizing. If massive galaxies existed this early, then supermassive black holes likely did too. We already know of quasars at redshifts above 7 hosting black holes of 1 billion solar masses. Those objects require extraordinary growth. Either black holes formed from massive seeds, perhaps collapsing directly from primordial gas clouds, or they accreted matter at sustained near maximum rates. Either scenario implies aggressive early dynamics. And black holes influence their galaxies profoundly. Jets from accreting black holes can heat gas, regulate star formation, and shape morphology. In early galaxies, those processes may have occurred on compressed timescales. Structure and feedback evolving almost simultaneously. It is breathtaking to imagine. Within a few 100 million years of the Big Bang, dark matter halos assembled, gas cooled and collapsed, massive stars ignited and exploded, heavy elements spread, black holes formed and fed, radiation rionized the universe, all within a sliver of cosmic history. And we once thought that era would look simple. Now, zoom out even further. The observable universe contains perhaps 2 trillion galaxies. If even a small fraction formed rapidly in the first billion years, then cosmic dawn was not sparsely populated. It was busy. Light was turning on everywhere. The darkness was short-lived. Webb is not just adding detail to our picture of the early universe. It is intensifying it. The beginning was not dim and hesitant. It was luminous and active. And here is the final emotional inversion. We often see ourselves as late as a tiny flicker at the far edge of time. But when we trace our origins backward through stellar generations, through galactic assembly, through the first enrichment events, we find ourselves connected to that early surge. The atoms in your body were forged in stars whose ancestors ignited in those early galaxies. You are built from matter that participated in that acceleration. From collapse, from ignition, from explosion, from recycling. You are not separate from cosmic dawn. You are its continuation. And that realization reframes the entire discovery. Webb did not show us a universe breaking its limits. It showed us a universe confident in its capacity. Confident that from faint irregularities it could build complexity quickly. Confident that gravity, given density, would sculpt structure decisively. Confident that physics, under pressure, could perform at scale. The surprise was ours. The capability was always there. And as Webb continues to look deeper, mapping more fields, capturing fainter galaxies, refining mass estimates, the story will sharpen. Some early claims will moderate, some will strengthen, patterns will emerge. But one truth is already secure. The universe did not crawl out of darkness. It ignited into architecture. Rapidly. Boldly. Within a few 100 million years, it was already shaping the structures that would one day give rise to stars like our Sun. And billions of years later, on a small rocky world orbiting one of those later generation stars, we built a mirror to look back at that ignition. We expected fragility. We found ferocity. And in that ferocity, we glimpsed the true character of cosmic dawn. There is a final scale shift we haven't fully absorbed yet. Because when we say massive galaxies formed too early, we're still thinking in comparison to today's universe to the Milky Way, to Andromeda, to the structures we know. But in absolute terms, the early universe was tiny. Not just younger, smaller. When the light left those galaxies 13 billion years ago, the observable universe was compressed to a fraction of its current size. Galaxies that are now separated by tens of millions of light years were once far closer together. Everything was nearer. Gravity's reach overlapped more aggressively. The cosmic web was tighter, denser, more interconnected. So imagine trying to grow a city in a vast empty desert versus growing one in a tightly packed valley with roads feeding in from every direction. In the desert, growth is slow, resources are sparse, expansion is measured. In the valley, supply lines converge, energy flows, development accelerates. The early universe was that valley. Cold gas streamed along filaments into dense nodes. Those nodes collapsed into the first galaxies, and because distances were shorter and densities higher, the inflow was relentless. Relentless inflow means sustained star formation. Sustained star formation means rapid enrichment. Rapid enrichment means even faster cooling and fragmentation. It is not magic. It is momentum. And once momentum builds in a gravitational system, it compounds. Now consider something even more destabilizing. Some of Webb's observations suggest these early galaxies were not only massive, they were surprisingly compact. That means enormous stellar mass packed into relatively small volumes. Compactness deepens gravitational potential wells. Deep wells retain gas more effectively. Retained gas fuels more stars. In such environments, the escape velocity, the speed required for gas to leave the galaxy, would have been extremely high. Feedback mechanisms that might disperse gas in modern galaxies could have been less effective in those early compact systems. Energy from supernovae may have vented along channels without unbinding the entire structure. Growth could continue, and the more compact a galaxy, the more intense its internal radiation field. The skies inside would have been dazzling, blue-white massive stars dominating the stellar population, ultraviolet light saturating space. Not gentle spiral arms, blazing cores. It challenges our emotional image of beginnings. We want the universe to start softly. Instead, it appears to have begun in brightness. Now zoom out again. The cosmic microwave background tells us the initial density fluctuations were small but sufficient. Inflation stretched the universe to near uniformity, but not perfectly. Tiny irregularities remained. Those irregularities were the seeds. From seeds, gravity grew forests. But in rare regions, those seeds were slightly larger. And in a dense, young universe, slight advantages compound quickly. It is the same mathematics that governs compound interest. A small head start becomes a massive lead over time. If a region collapsed just a little earlier than its surroundings, it could begin accreting matter while neighbouring regions were still near equilibrium. By the time the neighbours caught up, the early region was already far ahead. Webb may be observing those early investors of structure, and that reframes our discomfort. The universe did not violate its own schedule. It allowed for variability within it. But variability at cosmic scale produces giants. Now bring the human frame back into focus. We are accustomed to feeling small. We live on a planet orbiting a star in one galaxy among trillions. But there is another way to feel small, not as an afterthought, but as part of a vast accelerating process. When we say galaxies formed rapidly, we are saying the structure that eventually gave birth to stars like our Sun assembled quickly. We are downstream of early efficiency. The iron in your blood may trace its lineage back through stellar generations to those compact early galaxies. The calcium in your bones was forged in explosions that descend from that first cascade of star formation. You are the late echo of an early surge. And that is not insignificance. That is continuity. Now, step even further back. If the early universe was capable of assembling massive galaxies so quickly, what does that imply about the thresholds of cosmic evolution? It suggests that complexity does not require vast stretches of time once conditions are right. The delay is in the setup. The action is swift. Inflation a fraction of a second. Recombination hundreds of thousands of years. Reionization a few 100 million years. Galaxy assembly rapid once halos formed. The universe operates in bursts. Long periods of preparation followed by sharp transitions. And Webb is catching one of those transitions mid-stride. Not at the very beginning, not at the Big Bang, but at the moment when darkness was giving way to structured light. We expected dawn to be dim. Instead, it was industrial. Now, as astronomers refine redshift measurements and stellar population models, the numbers will settle. Some early mass estimates will shrink. Others will hold. But the qualitative shift is already permanent. We now know that by 500 million years after the Big Bang, the universe was not sparsely dotted with faint clumps. It was actively assembling significant structured systems. The cosmic web was alive. And that realization changes how we imagine the first billion years. It was not empty waiting. It was construction. And construction under pressure moves fast. There is something almost poetic about this. From near-uniform plasma to galaxies in a few 100 million years. From hydrogen fog to star cities blazing in ultraviolet. From quantum fluctuations to gravitational architecture, the universe did not hesitate at the threshold of complexity. It crossed it decisively, and 13 billion years later, on a quiet planet circling a stable star, we have the audacity to look back and measure that crossing. We built a telescope to find the first light. What we found was not fragility. It was momentum. And momentum, once unleashed, carries forward. Through galaxies, through stars, through supernovae, through planets, through life, through us. The early universe did not grow cautiously. It grew with purpose dictated by physics. Fast enough to surprise us, not fast enough to break its laws, but fast enough to remind us. The cosmos has always been capable of more than our intuition. There is one last edge to approach, and it is not about numbers. It is about perspective. For centuries, we have told the story of the universe as a long unfolding, a gradual expansion from fire to structure, from chaos to order, from simplicity to galaxies, then stars, then planets, then life. That story is still true, but Webb has sharpened its opening chapter, because the first billion years were not a slow prelude. They were decisive, and decisiveness changes how we feel about beginnings. Imagine compressing the entire 13.8 billion year history of the universe into a single year. January 1st, the Big Bang. By mid-January, the first stars ignite. By late January, according to Webb's emerging picture, galaxies with billions of stars already exist. By February, the cosmic web is well established. Everything else, the formation of the Milky Way's spiral arms, the birth of the Sun in September, Earth forming in mid-September, dinosaurs in December. Humanity in the final minutes happens inside a structure built almost immediately. The scaffolding was erected early, and that means the universe did not spend most of its life deciding whether it could build complexity. It proved it could, almost at once. Now feel that at a human scale. We often think our species emerged at the very end of a long cosmic patience. But if the universe demonstrated its structural capability in its first few percent of existence, then complexity was not a reluctant outcome. It was a rapid inevitability under the right conditions. Not guaranteed everywhere, but powerfully possible. The galaxies Webb sees are not outliers in defiance of physics. They are expressions of physics operating near its upper limits of efficiency. Dark matter collapsing in rare dense peaks. Cold gas flowing without interruption. Massive stars igniting in waves. Black holes feeding at near maximum rates. Radiation carving out bubbles in the surrounding fog. This is not a universe hesitating at the threshold. This is a universe pressing forward. And the more we observe, the clearer it becomes that the early cosmos was a place of extraordinary gradients. High density, high interaction rates, high energy exchange. Those gradients flatten over time as the universe expands. Distances grow, gas thins, star formation slows, black hole growth becomes regulated. We live in a calmer epoch, but calm is not the natural state of beginnings. Beginnings are compressed. Beginnings are unstable. Beginnings surge. Webb is showing us that cosmic dawn was not dim candlelight. It was a forge. And in that forge, galaxies took shape quickly. There is something deeply grounding about that realization, because it tells us that the universe did not stumble into structure. It organized itself. Relentlessly. From fluctuations so small they were barely measurable, gravity extracted order. From hydrogen and helium alone, it built star factories. From those factories, it forged the elements that would one day become oceans, continents, blood, bone. And it began that process within a few 100 million years. The timeline does not diminish us. It connects us. When you breathe in oxygen tonight, that oxygen's atomic ancestors were forged in stars that trace back through countless generations to those early galaxies. The calcium in your teeth passed through supernovae that descended from that first cascade of star formation. The gold in your ring was created in violent stellar events rooted in that early epoch of enrichment. You're not an afterthought at the far end of time. You are a late chapter in a story that accelerated from the beginning. Now zoom out one final time. The observable universe spans tens of billions of light years. It contains perhaps trillions of galaxies. Webb has only begun surveying it. Each deep field is a pinprick sample, and already we see evidence that the first billion years were more dynamic than we predicted. What happens when we map hundreds of fields? Thousands. What happens when next-generation telescopes, even larger, even more sensitive, extend our reach further back? The pattern will clarify. The extremes will be quantified. The models will adapt. But the emotional shift is already irreversible. The early universe was not timid. It was bold. It crossed the threshold from smooth plasma to gravitational architecture with urgency. And that urgency echoes forward. Because every galaxy we see today, including our own, is built upon that early scaffolding. The Milky Way did not assemble in isolation. It formed within a cosmic web that was already structured long before the Sun existed. When our solar system formed, it inherited a universe that had already proven its capacity for organization. We are beneficiaries of that early acceleration, and there is a quiet comfort in that. The universe did not require endless eons to demonstrate its creative power. It demonstrated it almost immediately, which means complexity is not a fragile accident waiting for perfect conditions. It is a natural outcome when gravity, matter, and energy interact at sufficient density. Webb did not discover galaxies breaking physics. It discovered physics unleashed under compression, and compression produces intensity. From the outside, the early universe might have looked like darkness. But inside that darkness, matter was collapsing, stars were igniting, black holes were forming. The silence was deceptive. The activity was immense. And 13 billion years later, the faint infrared glow of that activity reaches a mirror in deep space, a mirror built by a species born of that same cosmic process. We asked to see the beginning. We expected fragility. Instead, we found ferocity. Not chaos without rule, but order under pressure. Galaxies growing faster than we imagined possible, not because the universe broke its laws, but because it fulfilled them at scale. And as we stand here, small but aware, looking back across nearly all of time, one realization settles in. The universe did not hesitate to become complex. It became complex immediately, and we are living inside the consequence of that first, astonishing surge. Now we slow down, because after all the acceleration, all the density, all the ignition and collapse, we have to sit with what this actually means. Not for equations. For us, 13 billion years ago, in a universe barely awake, regions of slightly denser matter began pulling harder than their surroundings. Hydrogen drifted inward. Dark matter deepened the wells. The first stars ignited like match heads in a vast dark ocean. Then something extraordinary happened. The matches did not flicker out. They multiplied. Within a few 100 million years, gravity had assembled systems containing billions of stars. Black holes had already begun to anchor galactic centers. Heavy elements had begun seeding space. Radiation was carving transparency into the cosmic fog. The universe did not take its time deciding whether it could build. It built. And it built fast. Not chaotically, not impossibly, but decisively. The James Webb Space Telescope did not uncover a cosmic mistake. It uncovered cosmic confidence. Because when we say massive galaxies growing faster than physics allows, what we really mean is faster than our comfort allowed. Physics allowed it. Physics always allowed it. We just hadn't seen it yet. For decades, we looked at cosmic dawn through instruments that blurred its details. We assumed the early chapters were quiet, tentative, gradual. Webb sharpened the image, and the sharpened image revealed intensity. A universe dense enough to collapse quickly, a web tight enough to feed galaxies relentlessly, star formation efficient enough to cascade, black holes hungry enough to swell early. It feels like acceleration because it is, but acceleration within law is not rebellion. It is capability. Now zoom all the way out. Imagine the observable universe as it is today, 93 billion light-years across, filled with clusters, superclusters, voids stretching millions of light-years wide. That vast architecture rests on foundations laid within the first billion years. The scaffolding was not slowly assembled over most of cosmic history. It was erected early. Everything else, including us, unfolded inside it. And that changes the emotional weight of the story. We are not living at the end of a hesitant experiment. We are living inside the long consequence of an early surge of structure. The Milky Way formed within a universe already architected. The sun ignited inside a galaxy already matured. Earth formed from elements forged in stellar generations that trace back to those first star factories. You are built from matter that participated in cosmic dawn. The calcium in your bones, the oxygen in your lungs, the iron in your blood. All of it passed through stars that descend from that early acceleration. When Webb captures faint infrared light from a galaxy 13 billion years old, it is not just collecting photons. It is collecting ancestry. Light that began its journey when the universe was young, travelled across expanding space for nearly all of cosmic history, and ended on a gold mirror floating in the dark. And from that light we learned something essential. The universe did not crawl toward complexity. It leapt. The phrase faster than physics allows dissolves under scrutiny. Physics allows extremes. Given density, gravity wastes no time. Given fuel, stars ignite. Given collapse, black holes grow. The early universe had all three. And so it surged. There is something profoundly humbling about that. We often imagine ourselves as fragile accidents in a cold, indifferent cosmos. But Webb reveals a cosmos that was dynamic, energetic, and structurally ambitious from the beginning. Not purposeful, not conscious, but powerful. From nearly uniform plasma to blazing galaxies in a few 100 million years. From faint fluctuations to luminous architecture. From darkness to structure almost immediately. And 13 billion years later, on a quiet spiral arm of one such galaxy, we developed the curiosity to look back. That may be the most extraordinary part. The same gravitational processes that built early galaxies eventually built stars stable enough to host planets. Planets stable enough to host chemistry. Chemistry complex enough to host biology. Biology reflective enough to ask where it came from. The surge that formed those early galaxies set in motion everything required for this moment. Webb did not show us a broken universe. It showed us a young universe operating near its peak performance. It showed us that under compression, matter organizes quickly. It showed us that complexity is not shy. And it left us with something deeper than surprise. It left us with perspective. We are small, yes. A species on a rocky planet orbiting an ordinary star in a galaxy among trillions. But we are not separate from cosmic history. We are the late bloom of an early fire. The early universe built fast enough to astonish us. And that astonishment is a privilege, because it means we are witnessing the truth, not the assumption. The first billion years were not empty. They were incandescent. The galaxies Webb discovered are not violations. They are revelations. Revelations that gravity, given the slightest unevenness, will sculpt giants. Revelations that the cosmic dawn was not dim hesitation but blazing construction. Revelations that the universe, from almost nothing, moved with urgency. Now the pace slows again. The universe today expands quietly. Star formation declines. Galaxies drift farther apart. The wild youth has given way to long maturity. But we have seen the photographs of that youth. And they tell us something unforgettable. In the beginning, when the cosmos was only a fraction of its current age, it did not whisper its way into existence. It roared into structure, and we are living inside the echo